Hello, my name is Joseph Meyer, and today I will present an algorithm I developed with Munir Hiabu and Enno Mammen called random planted forests. I will first provide the setup for our algorithm, then I will introduce the algorithm itself and finish off by showing some simulation results. So the setup is a typical regression setup where we wish to estimate the regression function m. And as is typical, we impose some conditions on this function m, and the most important is the following. So we consider the ANOVA representation of m, and now we assume that the ANOVA expansion only includes interaction terms of maximum order q. Meaning, for example, if q is 1, we assume an additive model, so that all components are of the form mk of xk. The other extreme case, if q is d, there is no assumption on the regression function m. Additive models and models with higher interaction terms have been considered in the literature before. We'll not go into detail why these are important. And the other conditions are not as important. So we have some conditions like smoothness assumptions on M. So why do we need our new algorithm? Well, first of all, the algorithm is fully flexible in the sense that it also works when we use q is equal to d. So we have no additional assumption on the regression function. However, so the algorithm follows a structured path similar to the ANOVA expansion. Meaning, for example, if the true model is an additive model, it will actually return a model or an estimator which is very close to an additive model. Additionally, it is possible to constrain the model such that the algorithm always returns an additive model or an additive estimator. And this can be very helpful for interpretation, which is typically difficult in machine learning. So if we have the case where we return an additive model, this is very easily visualizable. So we can just draw the additive components, which are one-dimensional, and by that describe the whole function. Also, we have promising results in our simulation study and also have theoretical backing. So we have some consistency theorems we showed for our algorithm for a modified version of our algorithm, that is. And this is very typical in tree-based algorithms to consider modified versions where splits are done a bit differently as in the original algorithm. So now I want to explain an additive version of our algorithm. So where the result is always an additive model. And the more complicated version will just be hinted at later. So the idea is to simultaneously grow a tree for each coordinate k. And the tree may only be split with respect to its respective coordinate. And in normal tree-based algorithms, well, the tree is constructed to find a partition of the domain, and then the estimator is calculated. But in our case, it is important that we update the estimator in each iteration step. So when we build a finer partition, we also update the estimator in each step. So in the initialization phase, so in the beginning, our estimators are all 0. The residuals are just the y values minus the estimator. So it's just the y values in the beginning. And each tree is represented by a single leaf. Here it's just the whole domain, which we say is R. And now the algorithm constructs a tree for each component. Here it is, in each node, one split is made. And the height of the nodes describes when the split was made. So in the first step, the second tree was split. In the second step, the second tree was split. And in the third step, the first tree was split. And this makes a difference because of the updating of the residuals, as described beforehand. And this was a description how to construct a family of trees. However, similar to the random forest algorithm, in the end, we have a forest-based estimator. And the idea there is to just draw bootstrap samples from our original data and then apply the algorithm to these bootstrap samples with 2 additional conditions. When we look for a split, we don't allow the split to take place in any coordinate, but only in a predetermined, randomly chosen set of coordinates. And this is basically the same condition as in random forests. Additionally, we also don't allow the split point to be any split point, but only allow for the splits to take place in a predetermined, randomly chosen set. And intuitively, these conditions are sort of used to have less correlation between the families of trees. But one should also note that this second condition is required for our theoretical analysis, where we proved some convergence theorems. And in the end, the final estimator is given by the average of the estimators of the single bootstrap samples. So, and as I said before, this can be additive models can be used for visualization of the estimators provided. And here you can see that in a smooth case, our estimator does quite well compared to its competitors, whereas here a smooth version of some spline-based method is a bit better than our method. But our method also works well when we have jumps in the original function. These lines are just 100 or 40 simulations of a Monte Carlo simulation. So all just drawn over each other. And here you can see that our algorithm also does very well when considering jumps in the original regression function. And now I want to shortly describe what you do in higher order interaction terms. So the only difference is that now in each tree, you also allow splits with respect to other coordinates. So for example, in the third step here, the second tree was split with respect to the first coordinate, which means it results in a tree that is dependent on the first and the second coordinate. We still keep this leaf in the second tree though. So instead of deleting this leaf and adding 2 new ones here, we add 2 new ones here, but keep this leaf for further splitting. And this then can also be done for order 3 trees, order 4 trees, and order 5 trees. So the trees always come from lower order trees. Okay, and then shortly for our simulation study, I'll only skim through this. So if you're interested, you can just pause the video and look at it more precisely. We have a very typical setup where we use some regression function M, which will be defined more precisely on the slides to come. And one should also note that we have correlation in our covariates. So we have 3 different models we considered. First, we have an additive model with smooth regression functions. And here our algorithm did quite well, whereas the algorithms that used the assumption additive and smooth were a bit better than our model. Second, we used a model with interaction terms. It was the same model as before, but included some interaction terms. And there, our model did better than the competitors. And thirdly, we had an additive model, but this time the regression function had some jumps. And there, our algorithm also was very good compared to our competitors. So if you are interested in random planted forests, we have a preprint of our paper on arXiv. There will also be some to come where we also can consider classification. And also, if you just want to try our algorithm, you can go to GitHub and have an R code of our algorithm on this link. So thanks a lot for your attention and further enjoy the conference.